In this video, I go and introduce the rate of change and tangent line problems as a way to motivate calculus, and to introduce the limit concept, the basic building block upon which we will build calculus. So often students will say, what is calculus? Well, I guess the simplest way would be to say it's the way to study dynamical systems, something that's changing constantly, by investigating small changes of input and observing the outputs and trying to make a connection between the two. It might be better, though, to say the difference between Precalc and calculus. A good example is in Precalc, we would have the question, a car travels 20 miles per hour for 5 hours. How far did it go? Compared to in calculus, you would then say a car is constantly speeding up over a period of time from 0 to 5 seconds. At the end, it's traveling 20 miles per hour. Now, how far did it go? Now, in order to do this new calculus problem, we start with pre-calculus concepts. And then we use these ideas to approximate what we want to compute by looking at very, very small changes in quantities, typically, at least for Calc 1, for a long time. And then we use some kind of limit magic that allows us to create a calculus-based formula, which comes from a Precalc formula. Now, a good example of this was done way back when in Archimedes' times, when he wanted to know what's pi equal to. So he knew at the time that pi is the same as the area of a circle of radius 1, and he didn't know how to compute that thing because that's what pi is. So what he did was very clever, was to take from the center and draw radial lines out to the edge of the circle, creating a bunch of triangles. He made sure the triangles were all exactly the same triangle, and then he was able to find the area of a triangle and then just multiply by how many there were. That means then that pi had to be more than this number. And the neat thing is, the limit part of it is, he didn't do it once. He did it again and again and again, using more and more triangles, until, as you can see, he went to getting a pretty good approximation. He was able to get pi to about 2 decimal places using what he had back then, and that's amazing considering. So then the rest of today, I'll be going and showing you basic pre-calculus techniques to tackle 2 main calculus problems, and along the way you'll hear me say things like, as this gets close to that, that's the limit, doing a lot of hand waving. So the typical first example that any calculus student sees is the speed problem. Let's suppose that you want to know what's the average speed of some kind of particle or object that moves along a line. Now, pretend that the position of the particle is given by a function of time as time passes, and you can think of this function as actually representing distance that the object has traveled over that period of time, provided the object never turns around. So if it's always moving, say, to the right on the line, then the function is actually the distance that the object has traveled up to that point. So you can then define the average speed of that object over a time period by just finding the overall change in the function value, that'd be distance, and dividing by the overall change in time. So that'd be distance divided by time. You think of that as average speed. Let's do a small example. Let's suppose that a small ball has been thrown off a ledge and its distance traveled, y in feet, is given by a function of time, 16t squared, where t is the amount of time that has elapsed. I'd like to know what's the average speed of the ball over the time period for 0 seconds to 2 seconds. Well, that's not difficult to do. All you need to do is find the overall distance traveled, that's the difference in the 2 positions, or distances traveled to that time, and divide by the amount of time that has elapsed. That will then give you 32 feet per second. That's the average speed of the object over that time period. Let's try a more interesting question. This time I'm not interested in average speed. I'm interested in the speed of the object exactly at 1 second. Now that's more difficult because if I'm only dealing with 1 moment of time, no time passes, which means the object hasn't traveled, and therefore how can we compute the speed? So instead, we won't try doing it exactly, precisely right away. We'll just approximate it and see what happens. So let's approximate that speed by using the average speed, just over a really small period of time, from 1 second to 1 second plus a small bit of change in time. So that's from 1 second to 1 plus h, where h represents a very, very small change in time. You can then find the overall average speed over that time interval by finding the positions at that time. That's evaluating the function at 1 plus h and at 1, subtracting those two different positions to get the distance traveled, and to divide by the amount of time that has elapsed. In this case, over that time interval, the amount of time that has elapsed is h. Next, let's go ahead and consider what happens to this average speed when I use smaller and smaller time intervals. Now, it makes sense, hopefully, it seems reasonable, that if I use very small time intervals, the average speed shouldn't change very much, and it should be really pretty close to the true speed at 1 second. And notice that as the amount of time has elapsed, the time interval, as x getting really close to 0, notice how the average speed appears to be approaching a single number, which is 32. That part, that's me using the limit idea. We'll have to nail that down a little more later on. In the previous slide, I went and gave you a small justification that the speed of the object after 1 second was 32 feet per second. But I did so by using a table which had finite number of values in it. And then from that I gleaned that the speed must be 32 feet per second. That doesn't feel really good, not logically at least. So I'll provide you a more algebraic based argument. Here is the average speed of the object again. Just take this equation and just distribute the numerator, multiply it all out. When you do so, you'll notice that there's a common factor of 16. Just cancel those 16s, and then what's left over in the numerator, you can factor out the common factor of h. You'll then get this equation. Now remember though, h is not 0, because if it was, well then there's no interval, there's no time interval. There's just 1 moment, 1 second. So since h is not 0, I can cancel those common factors of h, giving me the function 32 plus 16h. Now that's the average speed over that interval for any elapsed amount of time h. So I can make that time interval as small as I want. So if I can make the time interval h as close to 0 as I like, 16 times that is as close to 0 as I like, 32 plus that is as close to 32 as I like. So it seems that I can make the average speed be as close as I want to 32 feet per second. I just have to make the time interval small enough, close enough to 0. Well, there must be a speed though. That seems reasonable. So then if there must be a speed, and this always approximates it, and all these approximations are getting close to 32, I'll just define the answer and say the speed of the object must be 32 feet per second. So that speed problem was an example of using an average rate of change to approximate a rate of change. Just to remind you, if you remember from your pre-calculus, the rate of change of a function with respect to x over an interval from x1 to x2 is just a change in the y values over the change of the x values. And using a small change in notation, if we say x2 is the same as x1 plus a small change in x, which we call h, then you can write the average rate of change of x this way instead, which is called the difference quotient. Now, if you want to, you can also interpret the average rate of change geometrically as the slope of a secant line that's between 2 points on the graph of the function. The point would be x sub 1 comma the function value at x sub 1, and the other point q would be x sub 2, and the y coordinate would be the function value at x sub 2. We'll see that this connection between these two concepts, an algebraic concept and a geometric interpretation, is pretty useful in order to go and do a number of our problems. To make that connection between average rates of change and secant lines a little more obvious, let's tackle the slope problem. So how do you find the slope of a curve, not a line? What we'll do is we'll borrow an idea from geometry. We'll use tangent lines. So if you have a circle and take a point on that circle and connect from the center to that point the radius, there is a single line called the tangent line that would then intersect that point at the circle once and only once. It would have to be at a right angle to the radii. But the important thing here is to notice that given that point, there's a unique line called the tangent line, which just nicks that curve. Because of that, since there's a unique such line, it's natural to associate the point with the tangent line and then the line with the slope. That means then that for every point on that circle, as long as you don't have a vertical tangent line, there's a slope to the circle. Now there's also another neat little feature. This tangent line, if you were to take a small box around the point and were to zoom in, you would notice there's very little difference between the circle, the arc, and the straight line. It's almost like the farther you zoom in to the circle at this point of tangency, that there's becomes less and less difference between the curve and the straight line. Considering the function f of x equals x squared, let's analyze the secant lines passing through the point 3, 9 in order to learn what we can about the tangent line. Well, I'll pick some other point, not p, on this particular function's graph. I'll pick where x is 4. That would then give me the point 4, 16. Now it seems reasonable that the slope of the secant line here should be about equal to, but not equal to, the slope of the tangent line. And it's easy for me to compute the slope of the secant line to change in the y values over the change of the x values. So the slope of the secant line should be about 7. Now obviously there's quite a bit of error there. Let's just do it again, but this time let's try to control how close we can get to the actual slope of the tangent line. So let's start at the point 3, 9. And let's use a very small change of x, giving us a corresponding change in y on the function. And the change of x we'll call h. So if we start at the point 3, 9, and we change the x-coordinate by h units, the new x-coordinate for our new point should be 3 plus h. And since I know the function is f of x equals x squared, I can find the coordinates of the point. Now that I have the coordinates of the new point, I can find the slope of the secant line as a function of h. It's just the change in the y values of these points divided by the change of the x values in these points. But if you just do that subtraction and then simplify it to your heart's content, here we'll have to use once again that h is actually not 0. So we'll have a common factor of h in the numerator and the denominator at some point, which we can cancel. Again, because h is not 0. That means then the slope of the secant line is given by the function 6 plus h. So if you tell me then how big of the interval, how big of a change you're going to use, well, I can tell you what the slope of the secant line is. But notice though, I can make 6 plus h to be as close as you like to 6 just by forcing h to be close enough to 0. So then all these values are really, really close to 6. When we know this, there is a tangent line, we know there is a slope for it. So then if there has to be a slope and all these things approach that particular slope, well then the slope of the tangent line must be 6. So I've now given you 2 different examples, one being the speed problem and one being the slope of a graph problem. But wait a minute, you should notice something. In each case, I wanted to compute something that required calculus. We then approximated it by using some kind of quantity. In the speed problem, I used average speed. In the tangent line problem, I used the secant lines. But each of those in the end boiled down to using a difference quotient in order to compute our values. And then we changed h to find out what happened. And as we did so, I would argue, and I can force this to be as close as I want to something. That part, that little sentence, that's the limit. That's what we need to discuss in the rest of this chapter so that we can apply the limit in order to do lots of cool calculus problems. And that introduces you to the 2 main problems that will motivate the beginning calculus for us, the rate of change problem and the tangent line problem. Don't worry, there's actually more problems beside this too, but that's towards the end of the course when we get to finally the fundamental theorem of calculus. In each of these 2 applications, clearly we need to talk about the limit. That's what I'll do with the rest of this chapter.